Yeah.
Hi again. My name is Leila. I'm from the Research and Data Team here at Media Foundation. Sitting in for Dario today, who usually does the show. Thanks a lot for those of you who are in the office and the Hangouts watching the old YouTube. We had some technical difficulties in the office, and now we're back. Thanks for joining us. So today we have two speakers. The first one is Aaron Halpiger from Research and Data. He will be talking about session designing, basically user sessions. And our second speaker is one of our collaborators, Bob West from Stanford University, and Ashwin, who is known for now in the Hangout, who will join us later. That research is focused on using traces, the navigation traces of readers to understand how hyperlinks should be connected, connecting Wikipedia articles. So without further ado, please.
Okay, let me get my slides going and I'll get started. All right, thank you very much, Leila. As Leila said, my name is Aaron Halfaker. I'm a researcher at the Wikimedia Foundation, and today I'm going to be talking to you about some fun temporal regularities in user activity sessions. Oh yeah, of course, my intro slide, I already said. I am a research scientist at the Wikimedia Foundation. Okay, so into story time. So back when I first started working for the Wikimedia Foundation in 2011, I was tasked with addressing this problem of the editor decline in English Wikipedia, basically trying to figure out why it was that newcomers weren't getting retained in Wikipedia anymore. One of the strategies that I employed in order to try and get a sense for what was happening to newcomers as they were coming to the site was to look at what I referred to as the first edit session. The first experience of editing Wikipedia after a newcomer registers their account. And to make a long story short, what I found out was that that first session is full of warnings and robots and that this was making newcomers sad. But I don't really want to tell you that story today. That's a story that I've told before. I want to talk instead about something that my collaborator, Stuart Geiger, asked when I first started talking to him about what this first session is and what it meant. And so the question that he asked me was, can you use this notion of a session to measure the amount of time that somebody spent editing Wikipedia? And so the place that this was coming from was this concept there's a wonderful essay on in English Wikipedia called edit countitis. Basically, the way that we measure somebody's contribution to Wikipedia as a project is by counting the edits that they do. But this is problematic because some edits are contribute more than others. Some edits are just harder to do than others. And so he wanted to get at a better measure for that. And so we did a bunch of work digging into ways to measure the amount of time that somebody spent working inside of a session. We developed a whole methodology around it, and we were able to eventually do some cool things in the end, like compare the total number of labor hours spent building Wikipedia to the total number of labor hours spent building major engineering projects like the Channel Tunnel, or to more traditional encyclopedias like the first version of Encyclopedia Britannica. And note that figure of 100 million labor hours for Wikipedia, that's actually super old. It's from March of 2012. If I extrapolate that based on the trends that we were seeing at the time, that should be more like 140 million labor hours now. So we'll probably overtake the Channel Tunnel in no time. But I really don't want to talk to you about that study. That's sort of old news. What I really want to talk to you about is the methodology that we use to actually get at this session stuff. All right, so part two of this talk is about methodologies. And so this is the part of the paper where everybody sort of like skips over because it gets into a lot of the nitty-gritty details, and usually you just wanted to know what the study was actually about. So we usually close our eyes and cover our ears once we see the methods section coming up. But I'm actually kind of a methods nerd. I really, really like this stuff. My favorite thing is to sort of argue about how it is that we can know things and what sort of methodological strategies are effective for that sort of stuff. So anyway, I'm really into this. I'm a methodology nerd. And And I think that this methodology bit is going to be particularly interesting for this audience. So the problem that we were looking at is session delineation. So let's say I have this timeline, and on this timeline for this user, they've performed a set of actions. What I'd like to be able to do is cluster those actions into sessions. Straightforward enough, right? So a common strategy for doing this is to measure the time between actions and set some sort of cutoff. And so I have these lines that I've drawn above the timeline that represent the time in between these actions on the timeline. And so let's say we draw our cutoff so that we grab those two long expanses. Then we end up with 3 sessions. But the problem here is that cutoff could be considered arbitrary. And so if we make that cutoff a little bit shorter, then we might pick up a couple of different interaction times, and now we end up with 5 sessions. So what's the right way to do this? Does this sequence of actions represent 3 sessions or 5? So this is what we supposed, is that if sessions are a meaningful component of human activity, we should see a natural cutoff emerge in the data, a natural best choice for deciding when a session has ended and the next session has began. So if we look at this time between events, I think that's where we're most likely to see this type of insight. So if I take those time between events and I throw them on the left-hand side here, we can build a histogram of how often certain times between events happen. And that's that plot that I was highlighting earlier. This is sort of capturing this time between events thing, where we can see that these long time between events, they represent values that are further to the right on the x-axis, where these short in between action event, or in between action times, are towards the left on the x-axis here. And so the cool thing that we found when we looked at Wikipedia editing using this sort of lens is that, oh yeah, and I forgot, before I get too far into this, I should tell the data junkies in our audience that this is an expectation maximization fit of a mixture model of 3 Gaussians on log scale data. Again, cover your eyes and ears. This is not what we're going to dig into. This sort of stuff is in the paper. We'll get to more of that later. Anyway. So back to these actual components that sort of appeared when we looked at the data, what we found is there was this sort of obvious long-term component, which we sort of interpreted as potentially being a between session time component. And there was this really, really strong short time component, which we conceptualized as within session. And so we just labeled those, this time component that's between 12 hours and 1 week as between session, and the time period that's between 1 and 7 minutes as within session. What we were surprised to find when we looked at this data was that there was this third component that was really far out there. It's really hard to see in the data, but the fit that we get when we run this expectation maximization is much, much better when we actually account for this third component. And it turns out that this is something that Wikipedians will find quite intuitive. This is an excerpt from the article on Wikibreaks. So it turns out that it's very common for editors to depart editing the encyclopedia when they go traveling, when their exams are coming up, when they get married or divorced, when there is a sudden change in regional weather, when they get a new job, that sort of thing. And enough so that there's an essay written about what this looks like. And of course, sometimes when editors depart Wikipedia, they also come back, such as coming back from traveling, your relative left your house, exams are over, that sort of thing. And just because I came across this as I was putting my slides together, this is a little hidden gem in Wikipedia. Another reason why you might come back to editing is you realize you hadn't died in the first place. Thanks, Wikipedia. Okay, so anyway, this long-term component seems to represent what Wikipedians refer to as a wiki break. And it seems to happen around the time scale of 1 to 12 months. So if you didn't notice this dashed line that's at an hour in this graph, that ended up being the cutoff that we chose for running this labor hours study in Wikipedia. So by discovering and being able to use and justify the use of this hour cutoff between these different components of activity, the within session and between session components, we were able to do a lot of really cool things, like reorganizing the list of top editors from those who did the most revisions to those who put in the most labor hours. And it turns out that some editors moved very far. if you'll notice that in the right list that's sorted by the number of labor hours, there's actually a lot of editors that don't appear in the left list. They weren't even close to the top 10, but when we look at the number of hours that they spent editing the wiki, they actually most definitely are in the top 10. We also found a lot of bots, because it turns out that bots look very, very strange when you measure their labor hours, because they tend to not sleep or eat or anything like that, and so they're always working on the wiki. And of course, we were able to do things like measure the total number of hours that went into editing Wikipedia. This is also a story that I don't want to tell. This is old work. I want to dig into exactly what this methodology means for the rest of the work that we might be doing. So if this worked for Wikipedia editing, shouldn't it work elsewhere? Why is it that we saw such strong clusters sort of jumping out at us in the data, and would we see those in other systems? So this is something where I started working with Oliver Keyes. And so we were digging into trying to figure out how we could see if this is just sort of like a thing that happens in editing Wikipedia, or it's more part of human nature, something that we might expect to see in other places. And so we worked together to gather data sets from 7 different websites that represent a very dramatic departure from editing Wikipedia. So we had AOL searches, we had page views on 3 different versions of Wikipedia from desktop, mobile, and app. We had route searches on Cyclopath, which is a computational GeoWiki. We had movie searches on the Movie Lens recommender system, and also ratings. We had change sets saved to OpenStreetMap, asking and answering questions in Stack Overflow, and playing games in League of Legends, which is a multiplayer online game. And it's for this reason that we refer to this thing as a mega study, because we brought together a bunch of collaborators and a bunch of data sets from a lot of different systems to try and learn whether the thing that we were seeing was generalizable. And so, as it turns out, when we looked at the data in these other systems in the same way as we did in Wikipedia, we saw some really strong regularities. In the data sets in this leftmost column, the bimodals, where we didn't really have long-term data, we found the within session and between session component, but we didn't see the extended break component. And that makes a lot of sense, because for most of these data sets, we couldn't track somebody long enough to be able to see an extended break. So for Wikipedia, of course, that appears in the extended break data sets, but also OpenStreetMap, because OpenStreetMap's history goes back long enough that we could see that extended break component come out. And it turns out that extended break component is more prolific, or more substantial in OpenStreetMap than it is in Wikipedia. And then finally, we also saw this short component come out when we looked at some of the data sets, where there was this really strong component that was appearing between 1 and 10 seconds. And so we also saw some data sets that didn't really reflect the pattern that we were seeing. We think that there are some good reasons why this sort of stuff didn't happen. Again, close your eyes, cover your ears, or look in the paper, whichever one you like best. What I really want to dig into is what we learned by looking at this short component and trying to see if we could explain what it actually was. So, looking at these graphs more closely, you can see that sort of light blue short component rising up above the dark blue within session component that we see in the other plots. As we were trying to figure out what this was, we ended up digging into theories of human consciousness as it applies to goal-directed behavior. And so there's this article that really needs some love if anybody has some time and interest. The activity theory article on Wikipedia is a really cool window to get at this stuff. There's a lot of complexity that activity theory looks like, but there's one bit of it that I want you guys to pay attention to, because I think it helps us explain this, which is that activity theory formalizes human actions in this hierarchy of an activity session, which contains actions, and each action contains operations. Operations are very simple things that you might do that are sort of mindless. They happen very quickly, like hitting a nail with a hammer. An action is more complex and is composed of operations. So say, for example, if I'm building a boat, I might hit many nails with hammers, but an action would be attaching this board to the boat. Whereas the activity session is the time I set aside every evening to go spend working on the boat, attaching boards, and hitting nails with hammers. I think that this metaphor applies really well to online systems, but the important thing is what this hierarchy implies. So if I take the same notion that we were thinking about before, which is the time between the logged events that we see in an online system, and I draw these interactivity times between the operations and actions that we see in this little diagram that I made here, it's pretty obvious that we can see that between operations, because they happen so fast, we'd expect to see a very brief interactivity time, whereas between actions, we'd expect to see a more substantial interactivity time. And so I think that that's what we're seeing in this graph, that it turns out that movie lens rating and movie lens search have a much tighter time component where we're actually capturing something like operations. And so the first question that I'd expect you to ask is, well, if operations come out of the data, why is it that we don't see it in Wikipedia editing? And I think that the answer here is AJAX, asynchronous JavaScript and XML, or in-page browser apps. So it turns out that movie lens rating and movie lens search don't require you to reload a page or anything like that in order to perform an action. So it lets you perform these sort of sub-operations really, really quickly and allows actions to happen at a different time scale. I still think that operations are happening in Wikipedia edits, but they're not logged in the database. So an operation in a Wikipedia edit might be copy and pasting text, looking up a reference, referring to some markup from another page, then coming back to the edit that you were trying to make and actually hitting save. It turns out that we don't log those operations, so they don't show up in the data. I bet you that if we did, they would. Okay, so finally, to bring this all together, what does this all mean? The most important thing that analysts can take from this is that sessions seem to be real things, and that this 1 hour cutoff seems to be a good rule of thumb, that almost every data set that we looked at, there was a very nice valley between actions that occurred less than 1 hour apart and actions that occurred more than 1 hour apart. And so you can probably, without even looking at your data, apply this hour cutoff and it's going to work okay. And regardless, applying our strategy, our methodology for looking at your data is pretty straightforward, so you can always do that too. But now on to a more grand note that I think is important when we consider what this means for human behavior and why I pulled in activity theory. So let's take an example of a new contribution interface like Wikigrok. So what I would suggest to the designers of new contribution interfaces like this is that you consider the activity session action operation hierarchy, and what our study implies about how these things manifest. That what I suspect will happen is that if you build your application so that it allows your user to perform operations in the scale of 1 to 10 seconds, actions in the scale of 1 to 7 minutes, and to return to the system on the scale between 12 hours and 1 week, that people will generally be more comfortable and get more out of using the system. That if you sort of force people to work at timescales that are different from this, you might inadvertently introduce some frustration. That's all I've got. Thank you very much. So, are there any questions?
Is on? Aaron, so I have a question about methodology. In particular, if you go back to the slide that showed the operation distribution.
So I'm sorry. Whoever has the mic, I can just barely hear you at all.
Real close. Okay. Hey, Aaron. This is Ellery. I have a question about methodology, and maybe to explain the question, it'd be nice if you could go back to the slide that showed 3 clusters, one with the distribution over operation time spans and action time spans.
Yeah.
Okay, so here,
there we go.
So looking at this data, the question that comes to mind is why you chose a Gaussian distribution. So the strange thing about the Gaussian distribution for modeling sessions is that it's defined from negative to positive infinity, right? So, and sessions are definitely things that are only occur a positive amount of time. So that's sort of one question about the Gaussian. The other is that it really looks like the short within and the within clusters, right? To me, that fit looks a bit forced. It looks like a log normal distribution. One log normal would fit that pattern far better.
So these are actually already log Gaussian distributions. So they're already log normal, and I wish I had the graph handy, but I would show you that actually one normal fits that very badly, or one log normal fits that very badly.
Okay, so we're seeing log data, and you fit a normal to the log data?
Yeah, exactly. So it's like fitting a log normal distribution.
Okay. Right. So I guess what I'm saying is fitting a log normal to the log data would look better, but that's getting a little confusing. So, sorry.
Yeah, and that very well could be. One thing that I might point out is that I think that in our other data sets, like we didn't push the cluster amount if we could get away with not pushing the cluster amount, but I think that we actually see this same sort of like skew pattern in other data sets. And so in this slide, you can sort of see in the AOL data set that I think that there's actually a short-term, like a shorter-term component in there too, but it's really pressed up against a minute, and I'm guessing that the reason that this is the case is that AOL search was fast, but it wasn't AJAX, and so it was just barely almost venturing into the scale at which operations occur, but wasn't quite there.
Next question.
Mm-hmm.
Hey, Aaron, this is Bob. I was wondering, how did you form your hypotheses? How did you decide you try a normal or a log normal? And have you tried any other models? And I'm asking because it has a flavor of survival times, the thing you're modeling here, or like inter-arrival times. And there are other distributions that are typically used for that, like Y-bull distributions and things like that. Have you tried that?
So no, I haven't tried a Weibull distribution, and you know what we might expect. Like, let's say that you know these sort of events were happening in time randomly. We would expect an exponential distribution for the time between activities, and so like I think that when we think about like what distribution we'd expect. Like that should be what we're looking for, but sort of there's human behavior that's pushing on the purely random distributions that we might expect to see. There's actually really long literature in trying to apply different methodologies to the time between like messages sent through text messaging systems, which is pretty close to what we're doing here. And it seems that people agree that generally you get the best fit with something that's sort of normal-ish. Like a lot of the work that I was looking at would mix Poissons, and I didn't quite understand why they were using Poisson. It sort of didn't make sense for the shape, and normal seemed to work quite well, so that's where we stopped.
Okay.
Aaron, here's one more question from IRC from Giovanni. The question reads, do you think that RC patrolling using Twinkle/Snuggle or whatever else is used these days would look more like an operation instead of an action?
Yeah, I thank you, Giovanni. I think that that's a really good idea. It's something that I really wanted to dig into, but it ended up, you know, other stuff got prioritized. So one place where I really think that our deployment of HHVM, which is like a performance enhancing strategy for basically it makes our PHP run faster. It will dramatically decrease like the page save times. And we didn't see a substantial change in like the engagement of new editors or anything like that when we released HHVM, but I bet you we would see some dramatic changes in those kind of fast operations that we would see in people who are using, you know, Huggle and Twinkle and that sort of stuff. But yeah, like I was saying, regretfully, I didn't have the time to look into that. I'd be very happy to collaborate with somebody who does have the time to dig into it. I can help you get data formatted in a way that makes sense.
Thank you. I think there are no other questions, so we'll move to the next talk.
All right. Thank you very much.
Okay. Hi, my name is Bob West, and I'm going to talk about mining missing hyperlinks from human navigation traces. So I'm a PhD student at Stanford, and I'm advised by Yuri Leskovets. And most of my research for the last years has dealt with Wikipedia. That's why I'm really excited that we could take this thing a bit more to a more formal level and start an actual collaboration with Wikimedia a few months ago, in particular with Leila, who did a nice introduction. The fourth person who's involved in this research is Ashwin, who's also on the Hangout. And he's actually done a lot of the work that I'm going to present here. Okay, so before I get started, or let me say, the reason I'm really excited about this collaboration, I think will come out in this talk because I start talking about work that I did before we started working together. And then the second part will be about how we can extend that work to work on data that comes from within the Wikimedia Foundation, and it's going to be a very natural transition. So that's why I'm really excited about this. Before I get started, let me make a quick announcement. We don't only work together in technical terms, but we're also organizing events together. So at the ICWSM conference, we will organize a workshop on Wikipedia, a socialpedia, research challenges and opportunities. And the deadline for submission is in a week. So if you have any preliminary work about social aspects of Wikipedia, please submit it there. 2-page abstracts are totally fine. All right, so let's get started. The motivation for my work is the World Wide Web, and specifically the part web of World Wide Web. What makes the web special is that it's not just a loose collection of documents, but that everything is woven together in a web. And these links that connect pages are actually a crucial aspect of the web. So for instance, from the user perspective, if I read up about Ingolstadt, which happens to be my hometown, on Wikipedia, I would read blah, blah, River Danube, and then I'd see, the Illuminati, a Bavarian secret society, was founded in Ingolstadt. And then I get curious about that, and I would simply click on that link, and I would read everything that's there about the Illuminati. Well, in the older days, what would correspond to this link click would be I'd have to put down my book, I'd have to go to another shelf, get another book, find the content in there. So the hyperlinks really make stuff easy. Then the links are also important from a search engine's perspective. For instance, the crucial breakthrough that Google made in the beginning that made Google popular was their ranking algorithm called PageRank after Larry Page, and that's based on the link structure of the web. So there's this paper that's called the 25 billion eigenvector, and it's called that because what PageRank really does, it computes an eigenvector of the weighted link matrix. So you see that without the links, Google couldn't rank anything. So the links are important. And finally, from a content provider's perspective, if there weren't any links, if I want to publish some content, but there is no link that leads to my content, then no one will be able to find it, neither users nor search engines. Okay, so let's look at links in the context of Wikipedia. Imagine I'm an editor and I write this new article about the Brittelbrunft, and a lot of concepts can't really be understood unless you put them in the context of surrounding concepts. So, for instance, you won't understand what a Brittelbrunft is if you don't understand what a pizzazz is or what a schpuzzle is. Okay, so what I would do as an editor would be, I call this target prediction. I would have to find appropriate phrases in the text, and I have to link them to the right article that explains that concept. And then on the other side, there is also the complementary problem of source prediction. This article that I'm writing won't be very useful if it's not linked from other articles, because people couldn't really find it unless they go through a search engine. The yellow task here, target prediction, is quite easy. Well, I mean, it's not super easy. You still have to know something, but when I say it's easy, I mean you only have to look at the text of the article, and you have to identify which are the link-worthy concepts and then link them. Source prediction, on the other hand, is much harder because everything can in principle be a source to link to Brittelbrunft. We'd have to check every single article and see if it mentions that concept and then decide if it's also link worthy. So if there are like 5 million articles, we'd have to go in principle through 5 million articles. So that's a much harder task. There has been a bunch of prior work on doing this thing automatically, because when I say 5 million, it's clear that no human can do that themselves. So it's nice if we have support from algorithms. And there has been prior work. The typical flavor of that is that these methods build a statistical model of the existing link structure, and then they use that to predict new links. So when I say statistical model, that could be things like pages that share at least 3 outgoing links also have a 50% chance of linking to each other. Reasoning like that. And when we, for a moment, step back from talking about hyperlinks, let's talk about an analogy in say, civil engineering. Let's talk about building roads, which could be considered links between cities. This classical view, where you build a statistical model of the existing links, would kind of be captured by the phrase, we build new roads that are in tune with the static structure of existing roads. So if I was a civil engineer and I would look, oh, cities that look like Modesto and San Francisco typically have a road between them, and I see a pair of cities somewhere else, then I would put a road there. That's what I call the static approach. But if you were a civil engineer, you wouldn't really do it like that. The way you do it is you would look at where the traffic is, and then you would get an idea where we need more roads. It's not really the structure, what the cities are like. It's really what the traffic between the cities is like that should tell us whether we build a new road. And I argue that we should do the same for links. We should look at where the links would be used and then put those links there, because the purpose of a link is to make navigation easier. If no one ever clicks a link, then it's kind of useless. Okay, so that gets us to part 1, where I propose a method for doing this traffic-based link prediction based on data that comes from Wikipedia, but not directly from Wikipedia, but we're collecting it explicitly from users by asking them to navigate Wikipedia. This is work that's going to be published soon in May, and this was done just before we started collaborating with Wikimedia. And then later in the second part, I'll show how we can extend this methodology to data that is collected by our server logs within Wikimedia. All right, so the idea of this approach is that we want to collect a set of navigation traces. We want to observe how people use the links to then predict where we should build new links. And we do this by designing a human computation game, which we call Wikispedia.net. A similar game is known under thewikigame.com. And the flavor of these two games is exactly the same, so I'm just going to lump them together here. The setup is this. You're given a start article and a target article on Wikipedia, and then you have to navigate from the start to the target just by clicking links. So we record people navigating from a given start to a given target that way. And to give you an intuition what this might look like is you come in, you see you're starting from start, then you go to the United States article because that's always a good one that's well connected. Then you continue to California because you know that a lot of fruit is grown in California. Then you click to orange because you think apples and oranges, both fruits, so probably orange will link to apple, but you can't find that link there. So you go back to California, you go back to United States, and you see, oh, United States links to agriculture, you go there, and then finally you find a link from agriculture to apple. Okay, so how could we use this data to predict new links? And here's the idea. Let's take user 1 in green here. He goes to the United States first, then he goes to the state. Does anyone know what this state is? Florida. And then they continue to orange because they expect this link from orange to apple to be there, but they don't find it. So they go back to Florida, and then they get frustrated and give up. And then the second user, might now in red, comes in. He also navigates to the United States first, then navigates to California, navigates to Orange because he expects the link from Orange to Apple to be there, but doesn't find it. Then from Orange to Agriculture, and then from Agriculture to Apple. So you see that two users now both went through Orange, which we can take as an indicator that they expected a link from Orange to Apple to be there, because we know that people explicitly tried to reach the Apple page. So that I take as an indicator that we should create the shortcut from Orange to Apple. And I'm saying this is based on traffic because we have an indicator now that the link, if it existed, would actually be used by people. So I'd say we should add it. So a bit more formally, the algorithm, I put this quote unquote because it's not really much of an algorithm. We start with a target that would be Apple in the example. Then we collect a bunch of these paths that are just sequences of pages. That would be down here it's just repeated from the previous slide. And then initially, we say every link that's a shortcut from anything along the path towards the target is initially a link candidate. And now we have to filter those. So you see that here. So it would be United States to Apple, California to Apple, Orange to Apple, Agriculture to Apple. And now we need to filter these because we can only put suggest a new link if the link doesn't exist yet. So we cross out from this list everything that already links to Apple. Agriculture does. And we can also only introduce a new link if the source page has a phrase that mentions the target, because otherwise we wouldn't know where to put the link. So we cross those out too. And then the only thing in this example that's left is Orange to Apple. But in general, we have many of these paths. So we need to somehow rank all the candidates we get from this method. And we can do that in several ways. For instance, we can simply count how often did people go through Orange when they tried to reach Apple and then rank by that. Or we can rank it by the kind of the semantic relatedness between the two concepts that we want to link. Okay, so in terms of evaluation, I'm gonna gloss over that. You can look at the paper if you want to. The gist is that it works quite well. It works better than some pretty strong baselines. The rest I'm gonna skip because we're kind of running short on time, I think. All right, but now for some discussion. What are some advantages of this method is that, one, we're addressing the source prediction problem. Remember, that's the one that's a bit harder because we have to check every Wikipedia page to see what could potentially be a source. And I'd argue we're optimizing the right objective here because we're really finding links that would make the navigability of Wikipedia better rather than just looking at the static structure of links and trying to generalize that. So that's, remember that civil engineer metaphor. And we can achieve that without really any model of link structure. So it's a very, you saw the algorithm, quote unquote, before, it's super simple. So I see that as a strength of the method. So we can do just some very simple rudimentary filtering and ranking and still it performs quite well. And why is that? It's because all the heavy lifting is done by humans. We tell humans now navigate to Apple, and then the human leverages all their common sense and expertise about the world to steer towards pages that they expect to have a link to target. So we just kind of exploit that thwarted expectation that humans have, and then the rest is simple. So that's why it's really it's human computation method, if you want. A disadvantage of the method, though, is that we need to know explicitly where the user is navigating. And in the game that we designed, this is easy because we tell them explicitly to do so. But in general, imagine we want to run this method on data that's collected passively on server logs. Then we wouldn't know any navigation target. It might not even be there. I'd argue that when people navigate Wikipedia, they don't necessarily have a target. They just often drift. So we need to, if we want to make this method more general, we need to find a way of doing it without knowing a target. And that brings us to part 2, which is about extending this method to data that is collected via the Wikimedia server logs. And this is ongoing work with Ashwin, Ure, and Leila. Okay, so the raw data we're using here are the Wikipedia server logs. So every time someone requests a page from Wikipedia, this is recorded on the server side, and it stores the timestamp, IP address, which page was requested, and also if the page was requested via a link click, we see what is the page where the link was at. So that's the referrer URL. And what we do then is we stitch together these referrer URLs and the page view URLs to construct these entire traces, these walks that people take on Wikipedia. And in general, they look like this. So imagine here, I come in, probably from Google, I reach the page, I want to learn about regression. So I start from the regression article, and then I first click to linear regression, but I also open in a second tab another link to nonlinear regression, and then from nonlinear regression I do another click forward to regression analysis. So in general, these navigation traces have the shape of trees, and we extracted all of them for 1 month of data for the 50 largest languages. And just to give you a sense of how big the data set is, for the English Wikipedia, we get over 2 billion trees like that for 1 month. Is that after? Do what we do? Deduping. How did we see duplicates in there? Oh, no, this is, right. No, this is not deduped, because I think the count information is actually important. If we see the several trace several times, that's an important piece of information.
Just to make sure, these are traces, but not single visits, right?
These are traces, exactly. Trace. So we have 2.4 billion of these tree-like objects. Okay, so how could we use these traces to find missing links in Wikipedia? Now the challenge, remember, is that we don't know what the navigation target was. And we don't even know if the user had any navigation target. But there's still a way of doing this, and the idea is to close triangles if justified by data. And what do I mean by that? Imagine that the user clicks from regression to nonlinear regression to regression analysis, and then if the data says that, if the stats kind of say that this is a good thing, then we want to introduce this shortcut from regression to regression analysis. So it's a very similar flavor to the game-based approach, but we now don't rely on T being the final target that the user tried to reach, but this could be within a navigation. The navigation could continue after T here. And we shouldn't just close all triangles. That would be too aggressive. But imagine that we see the following. Imagine that out of the times that users were on nonlinear regression, 5% of the times they clicked to regression analysis, and 95% of the time they clicked to another article. However, if we also know that they reached nonlinear regression from regression, if now all of a sudden the probability of clicking to regression analysis jumps to 34%, then we know that it's really S that drove the user to T, because everything else is equal. And so if we know that S drove the user to T, then that's an indicator that we should introduce the shortcut from S to T. So very simple intuition. So now let's see if this does anything sensible. So I call this results in quotes because we don't have any formal results yet, but we have some stuff to eyeball. So let's do that. What you see in this table is these triples, SMT. So that means the user navigated from S to M to T. And then here you see these two probabilities. That is, the first number is the probability of going from M to T, regardless of what S was, the page they visited before. And then here you see that probability when we know that they came from S. And so the first one is about the 2014-15 season of Bundesliga, which is the German professional soccer league. And then people went to Bayern Munich, which is a soccer club in Germany, and then from there they went to the 14-15 Bayern Munich season. And we see that in general, 5% of the times people click from Bayern Munich to the Bayern Munich 14-15 season, but when we know that they came from the page about the 14-15 season, then that probability is 23%. So there's a big boost. And it makes a lot of sense that people would navigate that way, because we already know that they have an interest in learning about this specific season. So it makes sense that they would then continue to that article. So that's definitely a good suggestion. The second suggestion here is also from the realm of soccer. These two gentlemen are Polish soccer players, and they're both goalkeepers. So here the user navigated from this Wojciech goalkeeper to Polish national team, and then to Artur Boruc. And the probability normally of navigating from Poland national team to Artur Boruc is 2%, but when people come from Wojciech, it goes up to 20%. So again, this makes sense, because this person probably was interested in learning about Polish goalkeepers. However, in this case, we couldn't even add the link to the page, because the page about Wojciech doesn't even mention Artur Boruc. And then the next example here is where someone navigated from the 2008 World Series to the 2007 World Series to the 2006 World Series. And again, we see a big boost. Normally, going from 2007 to 2006 is only 9%, but when we know that someone came from 2008, it jumps up to 80%. So that's huge. The reason for that is that the 2007 World Series article has this info box where you can navigate to previous and future seasons. So we see here that people just like to iterate through these lists. And another example is where we get a big boost for the link Federal Republic to Latin, because people like to have navigate in this triple Federal Republic, Federation, Latin. But that's really because Federal Republic has as its first link Federation, and then when you go to Federation, the first link is Latin. So we see that people just like to click the first links sometimes. Okay, so that was all pretty anecdotal, but let's do some discussion of what we have here. So I think these results are promising, and I think once we do a more formal evaluation, we'll see good results, and that's although we don't have any known target that the user is trying to reach. And I would argue that there are applications of this approach also beyond just suggesting new links. For instance, in mining typical browsing patterns. So we saw already in this in these few examples before that people like to follow first links. Now, in retrospect, you might say that's an obvious thing. Of course, people do that, but I didn't know that before. We now can get numbers. How popular is this pattern of first link navigation actually? And another thing is how popular is this pattern of iterating through lists? And there is a potential of mining automatically these typical patterns just by looking at these navigation traces. And I think if we know what typical navigation patterns is, that can help us to make the interface better. Another idea would be to do automatic suggestions for page restructuring based on these navigation traces. So remember that, for instance, in the example about these two Polish goalkeepers, we have strong evidence that there should be a link from Wojciech to Artur, but Wojciech doesn't even mention Artur. Well, maybe that is a sign that really Wojciech should mention Artur. So we have an indicator that maybe we should add not only a new link, but also new content to that source page. Another idea would be that if we see that a link is clicked a lot, but the link is actually at the bottom of the page, then maybe that's an indicator that that piece of content that encompasses the link should really be moved further up on the page. And the final idea would be to use these navigation traces to automatically construct reading lists or curricula. If we often see that people that are learning about say algorithms, have a certain sequence of pages, then maybe someone could come in and could say, oh, I want to learn about algorithms, and then we could give them suggestions for a good sequence, for a curriculum of what to read based on these navigation traces. And finally, we have a bot in preparation that that can add these links automatically. We're still deciding what the best way of doing it is, whether we should directly modify pages or whether we should add these suggestions to talk pages and wait for users to put them in, and so on. Okay, so to summarize, the motivation for this work is that links are key. They're very important, but they're often missing. And here we suggest a simple method to find missing links. How do we do it? We mine usage logs to basically guess which non-existing links were expected by the users that are browsing the site. And these are the links that we then want to put in. And in our first version, we use the human computation approach for that, where we explicitly asked users to navigate. That's done. And in the version 2, we want to adapt this method to passively collected Wikipedia server logs, and that's ongoing work. Okay, thank you.
Yeah, so I don't see any IRC questions, so we can take for now in-room questions.
So I had a few questions. So the first is, is there any thought on how for a trace represents a successful completion of a path versus an abandon?
I think that's a great question. That's something I want to look at. Because if we could answer that question, then we could basically backtrack even to the previous method, where we could, if we could identify whether the user had a specific target in mind and they accomplished that target, then we could say, okay, now we can run the other method. And also, I think just per se, it would be super useful to have an understanding of what is a successful Wikipedia session and what is a failed Wikipedia session. I think that's, yeah.
And the other two questions is more about the methodology. One, did you track if following links actually was a deep link into a specific section of an article versus just the parent article itself? And then the second part of that is, did a session include if someone were to not use on-site tools but go back and do external searches over the course of a session to find the content because they could not find direct links?
Okay, so I did not do these deep links. I strip out the hash, the anchor. Maybe it's something to consider because I guess it has some information whether the user was looking for something very specific. So that's a good point. And the other thing is, so currently sessions are or these traces are split in two as soon as someone goes to a non-Wikipedia page. So we would count as a new tree. But I totally agree that it would be useful to look to basically group these together and then take it as some sort of feedback that people weren't satisfied within Wikipedia if they had to go outside and do a search there. So that could actually be an interesting avenue.
Well, first a clarification. So when the bot would, when people are editing, it would suggest, oh, maybe you need to have a link to this other article. I mean, you're not proposing to just sort of slam it into see also section of a page or something.
Oh, I see. So currently we're thinking of actually putting the link onto the appropriate anchor text. So we would find which phrase could contain that link, and we add the link there.
Oh, wow. Okay. So in the case of California, you would try and find the word Apple in it and make that a link to Apple? Or?
That's right. Exactly.
Interesting.
And then we need to be careful, though, because in the context of California, Apple could also mean Apple Incorporated. So we are conservative in that sense, and we don't add a link if we're not very certain that it's an unambiguous link. And we get these statistics from the set of all links that are already in Wikipedia. So for Apple, for instance, we would know that say 30% of the time it goes to the company and 70% of the time it goes to the fruit, and that would not be enough for us. So we say we need a 90% confidence that the link would actually go to the target we have in mind. So the Apple one, we would probably just not, we'd not take the risk.
Okay. And my question was about disambiguation pages. Often people will they'll be reading about a band or something, and they'll search for someone in it, and then that'll take them to a disambiguation page. And right now, the disambiguation page, it'll say, I don't know, this football team, plays in Berlin. It's an English Wikipedia convention that the word Berlin there is not a link. The only thing that's a link on a disambiguation page is the page you're going to. And that's interesting because I bet a ton of people go to the disambiguation page. There's a word in there they really want to go to, but by policy, we don't let them. Did that come up in your research, or did you just not explicitly not look at disambiguation pages?
It hasn't yet, but that's because we haven't really looked too much at the data appropriate. So I'm very thankful for all these kinds of pointers, because one thing I'm excited about is to actually use this data to then feed it back and make Wikipedia better because of it. And this seems to be a great first point. So the idea would be then, I guess, to look and see if we find evidence that people actually expect that Berlin link there. And then if we have a lot of evidence, then we could say, all right, maybe we should revise certain policies.
Thanks.
So there's one question from IRC and a related question from me. So the question from Giovanni is, if people use heuristics like clicking on the first link, then perhaps not all missing links would warrant a real semantic relatedness. So do you think the method may end up adding too many links? And my related question was, have you done any sort of Crowder detection or filtering in this set?
Any what detection?
Crowder or robots.
Oh, I see. Yeah, so the first question, well, let me start with the second question, bots. We use the user agent library that has like certain bot filtering mechanisms built in, so we use that. It's not perfect, but so we're post filtering, or we're planning on doing that by deleting things that look suspicious in the sense of too many clicks too regularly. But that's going to be an ad hoc thing. And then the first question was, do we think that not all links might really be warranted? Because we just see those links in there due to certain navigation patterns that aren't really an indicator that people would expect that link. Yes, that's a challenge. So we need to figure out what are these navigation patterns, and then think about ways of separating them out. And I think even doing that, it's not just a menial task. It's actually something that is interesting and will give interesting insights, because we don't know yet what these spurious navigation patterns are. But we have some ways forward. For instance, checking whether something is the first link, that's easy. We can just look at the Wikipedia page. And also this list navigation. Here the idea would be, if a list is often traversed forward, then it's likely that it's also often traversed backward. So if we see this symmetry, then that might be an indicator that it's a spurious example. But the tricky thing is not how to fix those examples. The tricky thing is how to even come up with the whole space of these use cases. And that will be an interesting challenge.
I have a follow-up to S's question. How did you handle kind of the n-gram analysis or variations on words? For instance, like making sure that if you were to search to link a word, that goose and geese were the same, or that San Francisco and San Franciscans were the same. Yeah. Do you have a database that you're referring to for that?
So that is the approach we're taking here is based on Wikipedia, on the Wikipedia dataset, and namely on this mapping between anchor texts and link targets. So we say everything that in all of Wikipedia, as it is already, links to goose is a synonym for goose. And so you'll sometimes see the word goose that links to the goose article, but you'll also see the word geese that links to the goose article. So we just pool all these different synonyms, and that tends to work really well, actually.
So you're not currently using anything like Wikidata aliases?
No, no. But the reason is that the method we're currently using will encompass that, because the Wikidata aliases will typically also appear as link anchors at some point. And then we do additional things for discarding spurious anchors, things that appear very rarely. For instance, the letter A can be a link anchor to ampere, the unit of current. But most of the time that we see the letter A, it's really the indefinite article a. So we don't want to use that as a link anchor. And we do that by having a threshold on a link probability. Most of the time that a appears, it's not a link anchor. So we say if this link probability is below a certain threshold, then we throw stuff out. And these heuristics tend to work pretty well.
Okay. Thanks so much for everyone hanging around longer than 12:30. Everybody on Hangout and YouTube channel and in the room. This is the end of the March showcase. Thanks for joining.